Let's continue the discussion of the impact of uncertainty and outcome of climate policy. I'm going to talk about certainty equivalence. I said that when you're uncertain about the outcomes, you should focus on the expected damage rather than the best guess or something else. That is not quite true. What you really should do is focus on the certainty equivalent damage. The reason for this is that we're not interested in maximizing income, we're interested in maximizing utility. So how is the certainty equivalent damage defined? Well, first you stick the damages in your utility function. Then you calculate your expected utility. Then you take the anti-utility, you translate things back into money, because we're after all interested in a carbon tax or something which is expressed in money, not in utils. So we transform this back to money, and then we take the difference with our starting point, the starting consumption that we had if there were no impacts of climate change. This is the certainty equivalent damage, and as I said, this is a theoretically correct thing to do if you're evaluating things in utilities rather than in dollars. The difference between the certainty equivalent damage and the expected damage is called the risk premium. There's nothing to understand there, that's just a definition. Now, you may think I have a hole in my head. You may have thought it anyway, because the certainty equivalent damage, really what it does is it takes a utility, it applies a utility function, and then it applies the anti-utility function. So what difference does it make? Now, Jensen's equality will tell you it makes a difference, but it may perhaps be more intuitive to look at a worked example. So let's assume that there is a 50% chance of an impact of 10 and a 50% chance of an impact of 20. So our expected impact is 15. Now, let's evaluate this against an income of 1,000. Then what the certainty equivalent calculation tells you you should do is, this is your income of 1,000. This is the log of 1,000. So let's assume that we have, let's assume that that is a utility function. It's simply the log of income. So this is if there were no impacts. This is your utility. If there is an impact of 10, then you take 1,000 minus 10, take the log of that, that's 6.9. 1,000 minus 20, you take the log of that, that is 6.89. And then you take the average of these two, which is 6.89, and then you take the anti-log of this, the exponent, and then what you find is your expected equivalent income under this particular scenario with 50% chance of a loss of 10 and a loss of 20. And then what you see is that the income loss, or the equivalent income loss, is not 15. Income does not drop from 1,000 to 985, but it drops from 1,000 to 984.99. So your certainty equivalent damage is 1501 rather than 15, and your risk premium is 0.01. So what you see is, yes, it makes a difference. Is this a difference to worry about? No. So let's calculate a few additional scenarios. Here we evaluate things against an income, initial income of 100, so the impacts are 10 times as large relatively. This is your utility without impacts. This is with an impact of 10. This is with an impact of 20. The average of the two is 4.44, and that implies an equivalent income of 8485. Certainty equivalent of 15.15, and your risk premium is 15. It has grown, but it's still not something to get particularly excited about. Now let's focus on a different scenario where there's a 50% chance of an impact of 10 and a 50% chance of an impact of 98. So the average, the expected damage is 54. evaluated against an income of 1,000, the log of 990, the log of 902, the average of that, take the exponent, and what you find is that the risk premium has risen, right? It comes from 54 versus 55.02, so the risk premium is 102. Still, it's 2% or so, less than 2%. What are we talking about? Now do it against an income of 100, and what you have here is 450, just as we had before. But now this utility has fallen quite dramatically, right? Because we are approaching 0. So the average of these two numbers is 2.6, and now the income, the equivalent income is 13.42. The expected loss in income is 54, so you go to 46. But here you have only 13 left, and the certainty equivalent damage is 86.58, the difference between 100 and this number. And the risk premium now all of a sudden is more than 1/2 of the expected damage. So what is going on here? Well, we have a logarithmic utility function. We say that utility is the log of income. And what we have here is that income is approaching 0. So the utility goes to -infinity. You see the same thing in this graph here, where just forget about the green ones, just focus on the red ones. If we go, so this line here is the expected damage, this line here is the certainty equivalent damage, both expressed in money terms. And if we move from left to right, the impact of the catastrophe increases. The impact of the catastrophe increases from 0 with a chance of 1/2 versus the 10 that is there always, and of course it's 0.5. And then if the impact goes to 100, then, or the bad scenario, the impact goes to 100, then the average of 10 and 100 is 55, right? So that is this line here. The dashed line is the certainty equivalent, and if the impact is small relative to income, it's 5 relative to 100, and here it's 10 relative to 100, and here it's 25 relative to 100, then the certainty equivalent and the expected damage are almost the same. But if the impact goes to approach our base income, there is a chance that we lose everything. Then you see the two diverge. And actually I stopped drawing the curve here, because at 100 this curve actually goes to plus infinity, right? Because utility goes to -infinity. So if there is a chance that you're going to lose everything, that the impact approaches a total loss, then there is a big difference between the expected damage and the certainty equivalent damage. And in those cases, you need to do the theoretically correct calculation that is shown here, rather than as approximation, which is of course much easier, but valid only in a certain part of the parameters.